In this video, we're going to take a look at sequences. So let's just start out with the definition of a sequence. A sequence is a list of numbers that are written in a definite order. There's a few ways that we're going to notate that, but notice all of which include set notation, where we see these curly brackets. So there's kind of the long way of writing it, where we would list kind of each term of the sequence, and we would use ... to kind of indicate that the sequence either keeps going or we don't want to keep writing every single term, and so kind of we'll do a ... in between certain terms. A more condensed way to write that, and the more standard notation that we'll end up using for showing sequences, is this notation where a sub n would be what you could consider like the rule for the sequence, and then it shows the start of the sequence and the end of the sequence. Oftentimes we'll be interested in whether sequences converge or diverge, and we won't necessarily really care if like where the sequence begins, and so in that case we might also see this notation where we don't actually have like the beginning or the end of the sequence. So those are kind of three different ways that you'll end up seeing a sequence. Let's go ahead and jump into an example. So let's consider this sequence where it's 1, 1/2, 1/3, 1/4, etc. And a lot of this section is going to be about pattern recognition too, especially when you're given a sequence in its kind of more expanded form where you're just seeing every single term of the sequence. We might want to write that in the more condensed closed form. And in order to be able to do that, we have to recognize the pattern that the sequence has. So in this case, 1 is our first term, so we can indicate that with a sub 1. 1/2 is the second term, etc., up until where we happen to have listed the sixth term being 1/6. And then notice again the ... just shows that the sequence continues and continues. So for example, what would be the 27th term of the sequence? Hopefully you're seeing the pattern that's happening here with this particular example. What we're really doing is we're taking whatever the term of the sequence is, we're just taking 1 over that number. So for example, like a sub 6 is 1/6. So the 27th term of the sequence would be 1/27. And then that will help us to kind of bridge that gap between just having a list of numbers and being able to jump right to the closed form of the sequence where we would have the actual rule. The a sub n in this case is 1 over n. So now that we have that pattern recognition, we can write the sequence in its more condensed form with this notation. And that would end up being, using our set notation, 1 over n. And we need to figure out where, oh, I gave it away already, where the sequence begins and then where it ends. So we can see that the very first term is 1, so we can begin that at 1 then. And then it doesn't really end, it just keeps going, and so we would just indicate that it goes to infinity. If we had stopped, like here for example, just at the, from 1 to 1/6, from 1 to the sixth term, we would indicate that the same way, beginning at 1, but then I would put 6 as the end point. But that's not the case here. I just wanted to show you that extra example. Most of the time, our sequences will just continue on, and we'll have an infinity up here. Oftentimes, there's going to actually be more than one way you could write it in this condensed form, because if you take the beginning into account, you could end up changing your rule slightly. So for example, if you wanted to maybe begin your sequence at 0 instead, then you can kind of change your rule slightly just to make sure that your very first term is still 1. So maybe pause for a second and think about what that rule would be if you ended up starting your sequence at 0 instead. Okay, so if we started it at 0, we can see that the rule is still 1 over, right, something. We obviously still need to have an n. And in this case, we would need to have an n plus 1 so that our beginning would be 1 over 1 instead of being like 1 over 0. We can see that we definitely wouldn't want this to be a 0. And we'd have 1 over 0 as our first term. We don't want that to happen. That wouldn't be good. Okay, so you'll see as we go through some more examples, there's going to be more than one way that we can write the condensed form of a sequence. Let's take a look at that. Okay, so we've got lots of examples. We're going to go through 6 different examples here. And the first one looks kind of similar in its starting to the one that we just did. 1 1/2, but now instead of a third, a fourth, a fifth, it's 1/4, 1/8, 1/16, 1/32, ... So sometimes it can be helpful if the very first term is not a fraction, but the rest of them are. You can kind of think about writing the very first term as a fraction, just so that it's a little bit easier to see that pattern. So of course I could write 1 as 1 over 1, and then we can see the pattern a little bit better. So in this case, we have to kind of look, notice the numerator is always 1, which that's kind of nice. I'm going to start with that. I see the numerator is always 1. I don't really need to think much about that particular one. The denominator appears to be powers of 2. 2, 4. I multiply 4 by 2 to get 8. I multiply 2 by 8 to get 16. Multiply 2 by 16 to get 32. So it looks like we're doing powers of 2 here. So maybe 2 to the n. But then I'd have to think about where I need to begin my, my sequence. Notice if I were to begin at 1, my very first term would be 1 over 2 to the 1, which is actually 1/2. That is not actually the first term of the sequence, though. The first term of the sequence is 1. So again, this is the first term. Well, I guess we start at 0. This would be the second term of the sequence. So in general, we usually say that the first term is a sub 1, the second term is a sub 2, etc. And so, you know, you kind of, this is where the answers may vary comes in. You can start your sequence really wherever you want to start it. And in this case, if I started it at 1, I might have to just kind of, you know, tweak some things here. So starting at 1, I can see that it wouldn't just be 1 over 2 to the n, because then, again, my first term would end up being 1/2 instead of being 1. And so what we can do to change that is we can take 1 away in that numerator, so that now when I plug in 1 for n, I would end up having 1 over 2 to the 0, which does give me the first power. So just remember that anything to the 0 power ends up giving 1. So that's one option. If you feel a little weird about having that n minus 1 power, and you feel a little more comfortable about starting your sequence at 0, you could go ahead and do that. And then you could do the more, you know, intuitive pattern that we saw with it being 2 to the n power. And of course we'd have as our upper infinities here. Okay, so there's just 2 possible answers. Technically, you could have infinitely many possible answers, because you can always change your starting index and then just simply change the exponent to accommodate that particular starting point. Okay, let's move on to the next one. So here we have 0, 1/2, 2/3, 3/4, 4/5, 5/6. Okay, so feel free to at any time, if you want to pause it and kind of see if you can come up with these patterns on your own. That can be a great exercise, just to kind of see how that pattern recognition is going for you. So again, our starting one is 0, and so it might be good to write that as a fraction, just so that you can kind of see if there's a pattern going on in the numerator and then a pattern going on in the denominator. So I'm seeing that if technically I could write this as 0 over anything, but if I'm looking at the pattern in the denominators of 2, 3, 4, 5, 6, it makes sense to think of it as a 0 over 1 to begin with. Okay, so let's think about that. So this is again where you can kind of either start with a starting point or you can start with a rule. It can kind of be, you know, figuring out which one you want to go with first. I usually like to think of the rule first and then kind of go with the index from there, but they all should, you know, they should definitely go hand in hand. So I think, and actually now I'm going to do the opposite of what I said. I'm going to actually pick the index first, because I think that's going to be helpful in this particular case. So let's actually start with 1, and that way I can think of this as being the first term, this as being the second term, etc., like we do in our conventional notation. And so if I want a 0 in the numerator to begin with, I can see that it's just increasing by 1 every time. That's another kind of important thing. It's just going up by 1 each time. So this would have to be then an n minus 1, so that I start out with 0. The next one would be 2. 2 minus 1 is 1. 3. 3 minus 1 is 2, etc. The denominator is a little more straightforward even, because it's just going to be n. We can see it just follows the pattern of 1, 2, 3, 4, 5, 6, etc. Okay, once you write your closed form for your sequence, I definitely recommend that you kind of plug things in and see if it's working the way that you want it to. So you could even kind of rewrite the expanded form of the sequence once you have the closed form. So again, if I plug in 1, I'd have 1 minus 1, which is 0 over 1. That would be the first term. The second term would be now 2 minus 1 over 2. The third term would be 3 minus 1 over 3, dot, 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 and I can kind of give myself a little green check mark there, that it's doing what I want it to do. Okay, let's move on to part C here. Here's our first example of what we would call an alternating sequence, where it alternates in sign. So in this case, that's really all it does, is it alternates between -1 and +1, -1, +1. And there's a few ways that we can write this. The easiest thing to do in this case is to just write it in terms of an exponent, because if we think about taking a negative number to an even power, we get a positive. If we take a negative number to an odd power, we get a negative. So that's the easiest way to write these, and that's something that you'll end up seeing a lot when we have alternating sequences and later on alternating series. We'll get into what those are later. So in this case, we can kind of think of this as, we can start our sequence at 1 again. And so I need to take basically -1 to different powers in order to make this work. And we kind of see what that would need to be. So for example, like -1 to the first power would be -1. -1 squared would be +1. -1 cubed would be -1. So you can kind of see where this is going. This is going to create that alternation that I'm looking for in this particular sequence. And so where we would need to begin, well, notice it begins with a negative number. So I would need this exponent to begin with an odd power. And that makes sense then to just do n, because if I start my index already at an odd power, then that's the easiest way to do it. And let me just show you some other options, especially if you happened to pause and try to come up with some on your own. If you began at 0, what you would just need to do is make sure that this exponent, after plugging in 0, is an odd number. And so you could do that with an n-1. Well, I mean, technically it works. It'd be -1 to the -1 power, which would be 1 over -1. Might not be the easiest possibility. I think probably most of us would intuitively go with an n+1 instead, so that we'd have a -1 to the 1 power. Technically, you could begin this index. This one could be a 3, 5, 7, 9. It doesn't matter. You would be creating the exact same sequence. Okay, so there's some different options there. I'm going to go ahead and go down to D. Got my kind of thing, my right left off here. So in D, I've got 1, 3, 5, 7, 9. And notice, kind of similar with part C where we're interested in evens and odds, in this case D is an example of a sequence that consists of only odd numbers. So now we need to kind of think about how we would construct something that would always be an odd number. It might be easiest to think of how we would construct an even number first. So if you think about an even number, for example, 2, 4, 6, 8, ... these are all going to be multiples of 2, right? These would be, like, you could think of it as 2n. So remember, n, we're going to be plugging in whole numbers here, right? So n is 1, and then n is 2, and then n is 3. That would create this list of even numbers. If I want to create a list of odd numbers, what I can do is I can take an even number and then just simply add 1 to it, and that will create an odd number, or I could subtract 1 from it. So in this case, I can think of this as 2n plus 1, and then we could begin at, well, let's see, let's think about where we would need to begin if we did 2n plus 1. We would need to begin this particular sequence at 0, so that we would get 1 as our first term, and then keep going. If you wanted it to begin at 1 instead, we can think about how we would need to tweak that. So if I wanted it to start at 1 instead, if I plugged 1 in, I'd get 2. I need to subtract 1 in order to get 1 as my starting point. So that's what your sequence would be if you were starting it at 1 instead. Now some of these we might end up kind of bringing all together into, we might end up, if we didn't want this to alternate, if it was just 1 all the time, well, the easiest way to write it would just be 1. But if you wrote it as like -1 to the 2n, you could make it always be a +1. Or -1 to the 2n plus 1, you could always make it a -1. So sometimes we'll kind of combine some of these ideas. Actually, hopping back to part C really quick, another way you can create an alternating sequence is you can actually use trig functions also, because if you think about sine or cosine, they also alternate in value between -1 and 1. And so that's another option, just to show you that really quick. So if I had, you could use sine or cosine, doesn't really matter, just again, as long as you kind of make your starting point where it needs to be. Now, I don't want to have any like root 2 over 2s or anything like that in this particular case because it's just ones and negative ones. So if you think about what angles on sine make positive 1 and negative 1, I can see that it's the angle of pi over 2 that makes sine a positive 1, and the angle of 3 pi over 2 that makes sine a negative 1. And so we would need it to be multiples of pi over 2 in some way. Let me write that here, actually. But notice it's not just multiples of pi over 2, because like I don't want pi or 2 pi, because then I would end up having 0. So this is where creating an odd number might come in handy, because I want really just odd multiples of pi over 2. So we can make this 2n plus 1. And that will create odd multiples of pi over 2. I might actually go ahead and make this a minus 1 like we did in this example so that I can have it beginning at, so that I can have it beginning at 1 instead. So there's another way you could write this particular alternating sequence. Slightly more complicated, but just wanted to show that you could use trig functions as well to make an alternating sequence. Okay, taking a look here at E. We've got 1, negative 8, 27, negative 64, 125. So we see this as alternating. And again, we could use the trig function or we could use the exponent. I think this is probably going to be a little bit more intuitive for us to use. So let's start by creating the alternating component. Negative 1 to the... Now, if you don't know where you need to begin this at yet, what you could do is just put a little placeholder here to remind yourself, like, I need to make this something. I don't know if it's going to be an n or an n plus 1 yet, but we need to figure out a little bit more before we fill that piece in. And another thing we see is 1, the actual values. So this will create the alternating piece. The actual values I see are 1, 8, 27, 64, 125. And it might be helpful to write these in terms of powers instead, because I do see that they look to be cubics to me. I know that 8 is 2 cubed, 27 is 3 cubed, 64 is 4 cubed, and 125 is 5 cubed. So if you're not seeing that, sometimes you can just do like the prime factorization of numbers and kind of see, you might not be recognizing cubics, but that can be a good start. You can just kind of do the prime factorization of the numbers to see. So it's going to be, and notice what's happening is unlike this example, where it was like 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Notice in that case it's the exponents that are increasing by 1. 1, 2, 3, 4. In this particular case, it's not the exponents that are increasing by 1, but it's actually the base that's increasing by 1. So that means the base is going to actually be the increasing part. It's going to be the n value, and the exponent's going to stay the same. It's going to be the third power. So these are going to be n cubes. Now we'll go ahead and figure out where we want this to begin. If we're just going to go with a simple n cubed, I see that my first term is 1, so this would need to begin at 1. And then keep going, of course. And now here's where I'll go ahead and fill in my blank to figure out where I want this to begin. So if I just made this an n, then I can see that I would end up having a negative 1 as my beginning point because I'd have an odd power here, which I don't want. I want it to be a positive 1, which means that this needs to be an even number when I plug 1 in for n. And probably the easiest way to do that is with an n plus 1. Okay, of course there's multiple ways I could do that one. That's probably the simplest way I could write this particular sequence. Okay, let's take a look at F here, our last example before we move on to the next parts. Now this one's interesting. 0, 1, 1, 2, 3, 5, 8, 13, 21, ... So it feels different than the other ones in that it's not increasing by the same amount every time like this one was. This one was increasing by 2 every time, which is why our rule was linear, right? 2n plus 1. You can think of 2 as like being the slope. It's not, it doesn't seem exponential, nor does it seem like it's a power function. But if you kind of look a little deeper, and again, feel free to pause it if you're intrigued and want to try to come up with the rule on your own. It seems like if I take the 2 previous terms and add them together, I will get the next term in the sequence. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. You seeing it? 2 plus 3 is 5, and that pattern seems to keep going. 3 plus 5 is 8, etc. So it seems like what we do is we take the two terms to two previous terms, add them together, and we get the next term. I'm going to actually just write that out. Two previous terms added together gives the next term. Now let's think about how we would write that a little bit more mathematically. This is an example of what we call a recursive sequence, because the next term depends on the previous term. So oftentimes with a recursive sequence, what we'll do is we'll have to define the very first term of the sequence, and then the rule that we use to get the next terms. So for example, the very first term of this sequence is 0. I can see that here. Now the next term I can see is 1. Next term, 1. Next term, 2. So again, we add these terms together to get the next one. So I can see that what happens, actually let me do this one. I add those terms together to get the next one. So I'm taking the first term of the sequence, adding it to the second term of the sequence, and that gives me the third term of the sequence. So if we define this to be our a sub nth term, right, that's like the result that we end up getting out. The a sub nth term is given by taking the previous term. Now if you think of a sub 3, right, or the nth term, right, as being a sub n, the previous term would be the n minus 1th term. So you could write that as a sub n minus 1. This would be then the term before the n minus 1th term, which would be the n minus 2th term, I guess you could call it. So essentially I take the two previous terms, which you can denote as n minus 2 and n minus 1. I add those two terms together to get the nth term of the sequence. So that means that this sequence would have the rule a sub n equals a sub n minus 1 plus a sub n minus 2. Now notice that this on its own isn't enough. That is, if I just told you this is how the sequence is defined, you wouldn't be able to come up with the actual elements of the sequence based on just this definition. Because, for example, if I said, well, what's the second term of the sequence? Or I guess I'll do third term of the sequence. You go, oh, well, what you do is you take the second term of the sequence and you add the first term of the sequence. It's like, okay, that's great, but what is the second term of the sequence and what is the first term of the sequence? So when you have a recursive sequence like this, you need to indicate the rule, which is what we've done so far, but then also if your rule depends on, other parts of the sequence, you have to define what those initial terms are. So in this case, we would say we have this, and then we also need to say that the first term of the sequence is 0, and the second term, I don't want that there. I'll squeeze it in. The second term of the sequence is 1. So basically all of these together, and I don't usually like boxing my answers, but all of this is like a package deal. All of this together is what creates this particular sequence, which, if you are interested, is called the Fibonacci sequence. And it's oftentimes seen in nature. If you're interested in something like that, just head over to YouTube. When you're done with your Calc 3 videos and you have extra time, head over to YouTube and just Google Fibonacci sequence. It's pretty interesting. Quick spelling correction, especially if you're going to go Google this or put it in YouTube. It's actually 1 N and 2 C's. I always forget which one it is. Okay, now I have an exercise for you guys to try. So find that this is very similar to what we just did, except now you have two different examples to try on your own. So same idea, find the general form of the sequence and then write it in that closed form that we've been doing where, again, the K is the starting point of the sequence. So go ahead and pause the video right now and give this a try. Now, I want to make sure, I'm gonna do these right now, but it's really important that you pause the video and try it on your own, because watching math is generally pretty easy, but actually doing the math is much more complicated. So this is your opportunity in the video to kind of see if you've understood the things that we've done so far. Especially when it comes to pattern recognition, when someone tells you the answer to the pattern, it's like, oh, yeah, of course. But then coming up with the pattern on your own can oftentimes be a much different story. So go ahead and practice that pattern recognition, pause the video, and then come back once you feel like you have decent answers for A and B. Okay, so let's see how that went for you. Let's start with A. So again, we're going to kind of write this first term of 2 in more of a fraction form. I'm going to think of it as 2 over 1. And then we're going to just look at the numerator and the denominator separately to kind of see what's happening to each one. The numerator looks pretty straightforward to me. It's just increasing by 1 every time. 2, 3, 4, 5, 6. The denominator is a little bit more complicated, but nothing too crazy. 1, 4, 9, 16, 25. I recognize those as perfect squares. So let's put that all together. And I'm going to write here also, again, answers may vary, because depending on where you start your sequence, you might have a slightly different rule than I do. I think just conventionally, I think it's probably easiest to have it starting at 1. I've been pretty much doing that for most of these as we've been going. So I'm going to go ahead and start with that, beginning at 1. And then I clearly see that this rule involves a fraction in some way, so I'll go ahead and do my fraction. Let's start with the numerator, because again, the numerator is a little bit more simple. It's just increasing by 1 every time. So I know that my numerator is going to be something in terms of n. If it was increasing by 2 every time, it would be 2n. If it was increasing by 3 every time, it would be 3n. It's essentially just a linear thing. It's growing by 1 every time. It's not just going to be n though, because notice if I plug in 1 right now, I would get 1 for the numerator, and I want to get 2 for the numerator. So we're going to go ahead and do n plus 1. And now notice I get 2, and then when n is 2, I would have 3, etc. That is going to create that numerator that I'm looking for. Now the denominator, again, I am seeing that as powers of 2. If you aren't sure how to do that here, just write them out, write out the denominators as what they are. 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared. I realize this might seem a little tedious, but if you're not quite getting to that closed form right away, which is totally fine, we're building up that pattern recognition intuition. This is 1 squared then. We can see what's changing. We can see that the exponent's not changing. It's squared every time. It's the base that's changing. 1, 2, 3, 4, 5. That's going to be what our n is. So this is going to be n squared, and then I need to think, do I need to tweak that at all to make sure that my starting point of 1 is okay? I'm going to add my infinity there so I don't forget. It looks good to me because I plug in 1, I get 1 squared, which is what I was hoping for. Okay, so hopefully that matches. I'm just going to show you real quick, if you had maybe started yours at 0 instead, here's what that, actually I don't see why you would start it at 0. I think probably if you started it somewhere other than 1, you probably started it at 2 maybe? I don't know. If you did, then we can see the numerator would just be n, and then I would have to adjust the denominator slightly. It's still going to be n something squared, but now I would need this to be 1 when I plug in 2. So this would have to be n minus 1 squared. So there's 2 different ways that you could write that particular sequence, and there's more than that even. So, okay, let's jump over to B. This is an alternating sequence, so we can see that we need to do our little fancy -1 to the n. I'm not 100% positive if I want that to be an n or not, but I guess if I am starting it at 1, then I'm going to go ahead and, now that I have my starting point, I can decide whether I want this to be an n or not. And I do, because I want my first term to be a negative, and so I want my first exponent to be an odd number. And 1 is an odd number. So we're good there. Okay, and then another thing I'm seeing is that the numerator is always 1, and it's really, this is going to create the alternating piece here. Numerator is always 1, and then again I'm going to go ahead and write out the denominators. So 3 is 3 to the first power, 9 is 3 squared, 27 is 3 cubed, 81 is 3 to the fourth. So this appears to be, and I can also think of this as over 1, which is 3 to the 0 power. So I can see in this case it's not the base that's increasing by 1, but the exponent that's increasing by 1. And so it's going to be an exponential that we need to have in the denominator here. So 3 to the n, but I want my first exponent to be 0, not 1. So we're going to just do a simple -1, and then that should work. And so again, I want to remind you guys, I'm not going to write it out, but I'm reminding you that what I did here, if you're not feeling 100% confident in what you came up with, plug those numbers in for n and just kind of see if you're getting the exact same terms that you initially had. Okay, so now that we have a lot of examples under our belt, let's go ahead and kind of proceed forward and see how all this is going to start coming together. Okay, so one thing that we're going to be really interested in when we talk about sequences is not necessarily just having an expanded form and then using pattern recognition to write it in its closed form. A lot of times we'll actually be given it in its closed form, and what we'll be interested in is whether that sequence converges or diverges. Now you should have heard these terms before at some point, either in Calc 1 and or in Calc 2. Converges just essentially means that the limit exists, and diverges means that the limit doesn't exist. And a limit cannot exist in many ways. Either the values can just grow and grow and grow without bound, and in that case we would say that the limit is infinity and that diverges. Oftentimes, or other times, we can just have it be not approaching a single number, and so that can be another way that a sequence can diverge. So of course we're going to be looking at limits. When we have a sequence, especially a sequence whose end is infinite, which we'll be looking at all of those, that'll be the case in all of the examples we look at from this point forward, we'll be looking at what happens to that sequence as the n values increase without bound. So do the terms end up approaching a value, or do the terms just grow and grow and grow, or do they just seem to bounce around and oscillate? Okay, so those are some different things that we'll be looking at. And again, these two terms are going to be extremely important in this class. We're going to be talking about convergence and divergence a lot. This is just the beginning of that. So if you oftentimes get those two words confused, a lot of times what I think of is the word converge pretty much means come together. And so you see then that the terms are starting to approach something. It's coming closer to something. Diverge pretty much means like to go away from each other. Like if two cars are diverging, they're moving farther away from each other. If they're converging, they're getting into an accident potentially, or they're just coming closer to each other. So another way you could remember it is converge is generally a good thing and diverge is a bad thing. Diverge starts with die. Dying is a bad thing. So if you kind of get those confused at all, just those are some ways that you can help to remember that. Okay. Most of the time what we'll be interested in is just whether a sequence converges or diverges. But beyond that, what we can also do is if it's a convergent sequence, we oftentimes want to know what does it actually converge to. And in order to be able to determine that, we're going to have to use a lot of the previous information that we had in, especially in Calc 1, because notice we're doing limits, right? Which is what we did in Calc 1. So let's take a look at an example. Now we're going to actually go back to all those examples that we did, and we're going to determine whether those sequences converge or diverge based on looking at the limit. Now if they converge, let's actually find the limit, what it ends up converging to. And by it, I mean sequence, what the sequence converges to. So coming back up here to example 2, I think I'll go ahead and use a different color here. We'll go with purple. Okay, so now it doesn't really matter where a sequence begins. That won't affect its convergence or divergence. So really it's just more figuring out what happens to the rule as n approaches infinity. And so really you can do that in any of these particular cases. Like you can take any of these rules. I think what I'm going to do is I'm going to do all the ones that start at 1, because I think that's kind of the more conventional starting point for our sequences. And then and we'll go ahead and do the limits. So let's start with A here. I'm going to take the limit as n goes to infinity of 1 over 2 to the n minus 1. Okay, so in evaluating this limit, there's a few ways, if you remember back to Calc 1, there's lots of ways that we can evaluate a limit. But overall, what we kind of think about is the first thing I want to make sure we don't do is plug in infinity, because infinity is not a number. We're not just going to plug it in and see what happens. But we can kind of like theoretically think about what happens to this expression as the n values get larger and larger and larger. And a lot of times it can even be helpful when you're determining whether a sequence converges or diverges. This kind of expanded form can actually be very helpful in determining that. So notice that as we go from one term of the sequence to the next, it decreases in value, right? I've got 1, and then it decreases to a half, and then it decreases to a fourth, and then an eighth, and a 16th, and a 32nd. The next one would be 1/64th, etc. They keep getting smaller and smaller and smaller. But they're definitely not going to become negative at all. So it seems like these terms of the sequence, they have this lower bound of 0, that the terms of the sequence are never going to go past 0, and they're also never going to actually be equal to 0, but they will be getting closer and closer and closer to 0 as our n value increases. So we would say then that this limit equals 0, and since the limit exists, then that means that the sequence converges. And specifically, we can say that the sequence converges to 0. Okay, looking at B, again, we're going to take the limit as n goes to infinity of the rule, the expression that, that we use to create the terms of the sequence. So n minus 1 over n. Okay, so again, we're not plugging in infinity here, but if we kind of think about increasing numbers for n, what we essentially will have is an increasing without bound number in the numerator, and then same in the denominator. So we'll essentially have the indeterminate form of infinity over infinity. And there's a few ways that we can tackle an indeterminate form of infinity over infinity. So if you remember, L'Hopital's was a great rule to use when we had an indeterminate form of 0 over 0 or infinity over infinity like we do in this case. So let's try L'Hopital's rule, and I'm going to show you another way that we could evaluate this limit without L'Hopital's rule. So just a quick refresher on L'Hopital's rule. First thing that we need, well, I should point out when we do L'Hopital's rule, the function needs to be differentiable, which implies that it needs to be continuous. Notice that when we look at a sequence here, these sequences are not continuous. That is, if you were to graph a sequence, which we're going to do later, it's just distinct points. It doesn't create an actual curve like a function does. So, but we're going to kind of bend the rules a little bit, and we're going to just go ahead and apply L'Hopital's rule from here, because our goal really is to evaluate this limit, which we can do based on it being an infinity over infinity form. So I'm going to use LH over the equal sign just to indicate that I'm applying L'Hopital's rule to get to the next step. So if you recall L'Hopital's rule, it says we take the derivative of the numerator and the derivative of the denominator. In this case, I'm taking the derivatives with respect to the input variable, which is n. So taking the derivative of n minus 1 with respect to n would just be 1. And then the derivative of n with respect to n would also just be 1. So then I get the limit as n approaches infinity of 1, which would of course just be 1. 1 is not affected by n in any way, so it's just the limit of a constant. Another way we could do this one without using L'Hopital's rule, and I think maybe I'll do it up here where I have a little bit extra space, is we could split this up into two fractions, because we have this subtraction in the numerator. So I can write that as n over n, which is 1, minus 1 over n. So technically this could also be the rule for the sequence. You could rewrite this as 1 minus 1 over n, and you would still get the same terms of the sequence. It's just not quite as intuitive. But algebraically, it's the same thing. Now looking at this limit, I can see that the limit as n approaches infinity of 1 is just going to be 1. As n approaches infinity, 1 over n is going to get smaller and smaller and smaller and approach 0. So this limit will end up being 1. And notice we get the same thing either way. So in this case, this would be using algebra. This would be using L'Hopital's rule. Either one works. And either way, we see that this sequence converges to 1. Moving forward, part C here, we have our alternating sequence. Either one that you end up looking at here, if you do the limit as n goes to infinity of negative 1 to the n, Now you can think of this a few different ways. Notice, for example, like as n approaches infinity, I'm just taking -1 to that power. Now, infinity is not a number. It is neither even nor odd. So I can't really say whether this is going to be something, of negative value or positive value. What's going to happen is it's just going to kind of keep oscillating around between -1 and 1, which we can see in this more expanded form of the sequence, that the terms don't appear to be approaching anything in particular. They just keep going between -1 and 1. Unlike up here, where if I look at the terms, I can see that as we kind of proceed this way, the terms themselves are getting smaller. They're decreasing in value and getting closer and closer to 0. Here, I can see that as we increase our n value, what happens is, 5, 6, 6, 7, 7, 8, 8, 9, all of those fractions are getting closer and closer and closer to 1, which is what we see as the resulting limit. In this particular case, these terms themselves aren't actually approaching any particular number. So what we would say then is that this limit just doesn't exist. You can use DNE. So since the limit doesn't exist, then we would say that this sequence diverges. Okay, moving on to part D here, 1, 3, 5, 7, 9. We can do a formal limit here of this was our one that began at 1. But again, you could do either one of them. But you can see what happens is as n gets larger and larger, I multiply that number by 2 and subtract 1. It's still going to be increasing without bound. This is going to approach infinity. You can also see that when you just look at the terms of the sequence. They just increase by 2 every time, and there's not going to be any limit to that increase. It's just going to keep increasing and increasing without any bound. And so this limit is infinity, and so we would say that this sequence diverges. Okay, part E here. Kind of similar. This one actually is almost like a combination of C and D. Not only does it alternate like C does, but the absolute value of the terms also increases without bound, like what was happening in part D here. So you could look at this in terms of a limit. Let's think of how that would play out. Okay, so if I look at this limit, now if you just look at the n cubed part, that limit would be infinite, right? Plug in a number that's growing without bound, we're going to just be getting an even larger number since we're cubing it. But since it's alternating, we can't really say whether this would be so without this piece, we could say that this limit is infinity. But since it's alternating, we can't really say whether it would be a positive infinity or a negative infinity. It would just keep kind of oscillating between really big negative numbers and really big positive numbers. So this limit just simply doesn't exist. And this is another example of a sequence that diverges. F is a little bit more tricky because when you're determining whether a recursive sequence converges or diverges, there really isn't necessarily a limit to actually evaluate because it's not like a rule, right? We don't have a single expression that produces the terms of the sequence. Instead, the terms of the sequence are constructed based off of previous terms. But what we can do is just simply look at the more expanded form of the sequence and see, since the way that we create the next term is by taking the 2 previous terms and adding them together, it's just going to keep growing and growing and growing. So you could write this then as the limit as n approaches infinity of a sub n. Notice I'm not writing any sort of closed form expression here, just writing a sub n as being the nth term would be infinity because the terms would just keep growing and growing. And that's for this one here. So the Fibonacci sequence diverges. Okay, let's have you pause and go ahead and do A and B for exercise 1. Again, this is your opportunity to kind of test out your limits, figuratively and literally, and kind of see how you're feeling so far with the content. Okay, so in part A, we're going to look at the limit as n goes to infinity. And I mentioned I was going to do the ones that started with 1, so let's do n plus 1 over n squared. Okay, and we can see that this is another example of where if you kind of think about letting n grow and grow and grow, the numerator is going to increase without bound towards infinity, and so is the denominator. But notice the denominator has a squared, and so the denominator values are going to always be larger than the numerator values. And you can, well, not always. that's the one where it's not the case. But you can see as it keeps going this way, we end up seeing that the denominators are increasing in value much more quickly than the numerators are. Okay, but we have infinity over infinity in this case. And so what we can do is we can apply L'Hopital's rule. Again, derivative of numerator, which is 1, derivative of denominator, which would be 2n. And now we can see that as n gets larger and larger, we'd have 1 over 2 times that value. That is going to just keep getting smaller and smaller in value, and we'll have a limit of 0. Another way you could do this one in a more algebraic way, instead of L'Hopital's rule, is again kind of thinking of it as splitting up that fraction into 2 fractions, n over n squared, which is 1 over n, plus 1 over n squared. And notice that in both of these cases, as n approaches infinity, 1 over n will get smaller and smaller, and so will 1 over n squared, and I get a limit of 0. Okay, so either way you look at it, we would say then that this sequence converges. We had done so many diverging ones. Okay, part B here. We're going to again take a look at the limit as n approaches infinity. Now of -1 to the n, 1 over 3 to the n minus 1. Okay, so now with this one, this one's a little tricky because if you think about this one, this is going to be that alternating piece that keeps going between -1 and 1. And that has been an issue before. So far, all of our alternating sequences have diverged, which have been part C and part E here. Notice both of those diverge. In this case, though, let's just take a look at the non-alternating piece. If we just take a look at the limit as n approaches infinity of the 1 over 3 to the n minus 1 part, we can see that the numerator is always 1. The denominator would keep growing and growing and growing without bound. So this would tend towards 0. Now if you think about that fact, the fact that the terms, the absolute value of the terms are approaching 0, it really doesn't matter whether it's a positive or a negative because, right, 0 has no sign. So you can see that each term is going to be, it's going to be alternating, but the absolute value of each term is going to be getting smaller and smaller and smaller. So this limit actually ends up being 0 as opposed to like D and E, because again, there is no sign to 0. The terms themselves are just going to keep getting smaller and smaller, whether that be from underneath with negative value or from above with positive value. We're still going to see those terms getting closer to 0. So this sequence converges. Okay, hopefully you felt okay with that when you were doing it on your own, and let's keep moving forward. So now that we've talked about convergence and divergence, let's kind of explore a way that we can visualize these sequences. And I don't know about you, but I'm a very visual person, and so if I can visualize something, it really helps me to better understand the concept in general. And so if we can visualize a sequence, we can maybe also visualize whether a sequence converges or diverges, or be able to use that graph in order to be able to help us determine that. So there's 2 primary ways that you can graph a sequence. You can graph it on a number line, or you can graph it on our usual Cartesian plane, our rectangular coordinate system. In this case, it wouldn't be an x-axis and a y-axis, it would be an n-axis, which would be the horizontal axis, and then your vertical axis would be the outputs, the results, the elements of the sequence, which would of course be a sub n. Okay, so let's start with an example. N over n plus 1, and our starting point is at 1, and it keeps going. And now we're going to go ahead and graph this. We're going to graph on a number line, and we're going to graph on the Cartesian plane. So let's start with the number line. Actually, I like blue. Okay, so number line. Now this is going to be, okay, so we're going to label this number line. What we're going to be plotting along this number line are the elements of the sequence. And so this number line is going to represent a sub n, the resulting elements of the sequence. And you can kind of orient it however you want to. You could kind of make 0 the middle point if you want. But another thing you can do is kind of look at the rule or expression of the actual sequence. And I can see that this is never going to be negative. It's not alternating. So I don't really need it to begin. I don't really need 0 to be my center. I can kind of shift 0 over here because I don't really need to put anything over on this side. Okay, and then let's just start plotting, and then we'll kind of decide where we want to put more of our number line. So let's just start with, what might be a good way to start this is to actually, you've got your closed form of the sequence. Now let's actually write it in its expanded form. Plugging in 1, I would have 1/2. Plugging in 2, I would have 2/3. Plugging in 3, I would have 3/4, 4/5. We'll do one more, 5/6, etc. And so this would be the first term of the sequence. Second term. I know this is a little tedious right now, especially as we do this for the very first time. We want to make sure we are very clear on where all these pieces are coming from. Okay, so let's start with, so now that I have all of these, I can kind of see what's going to happen. It looks like I don't think my values are going to get any larger than 1. It doesn't appear to be the case. So I'm going to make this 1. And now it does get a little tricky to graph this when you have all these different denominators, but we'll do our best. So I can see the very first term of the sequence is 1/2, and I'm going to label that with a sub 1. The second term of the sequence is 2/3, so I can kind of split this into 3 pieces. So this would be 1/3. I should probably label these. I think I'll actually write a sub 1 at the top instead. 1/2, 2/3. Okay, and then we'd have, so a sub 2 is 2/3. Okay, a sub 3 is 3/4, which would be halfway. And now if your number line's not perfectly scaled, like mine is, mine's perfect, no, not really, then, you know, just do your best. So in this case, so a sub 3 is 3/4, and I think I'm going to go ahead and stop splitting it into its perfect fractions now. 4/5, I know, would just be a little closer to 1. There's a sub 4. A sub 5 would again be a little closer to 1. It would be exactly halfway between 2/3 and 1. So if you do want it to be kind of somewhat precise. Okay, and you could keep going from there. Now obviously we're not going to graph every term of the sequence, because that would be impossible, because it keeps going. But the idea is that what happens is, as we continue graphing the terms of the sequence, we can see that the terms themselves are going to keep getting closer and closer and closer to 1. So I'm just going to label that one as a sub n. Well, I don't like that. I'm just going to label it as a sub 10. That's roughly where it would be. So we can see that as n increases, our sequence, the terms of our sequence, are going to be getting closer and closer and closer to 1 on a number line. So hopefully you can see why we would do this. Like, why would we graph a sequence? The graph tells me a lot of things, like most graphs should. In this particular case, I can see that as I increase my n value, the terms are getting closer and closer to 1, so I can visually see 1, sorry, I meant to do a color change. I can visually see 1 as the limit of the sequence. I can see that the limit as n approaches infinity of a sub n is 1. And notice that I found that visually without having to do L'Hopital's rule or algebra or anything like that. I can see that the sequence is going to converge. Now let's take a look how we could represent this on the rectangular coordinate system, the Cartesian plane. So in this case, now what I'm going to have is a two-dimensional view of the sequence, where I'm going to have n as my horizontal axis and a sub n as my vertical axis. So this is where you can kind of go as far as you want to on this particular horizontal axis. I guess it depends on how motivated you're feeling. I think maybe I'll go to 10 because that's kind of about how far I went to on here. But like I said, you can kind of decide as you go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then just like when we were trying to figure out what we needed to do with our number line, we'll be doing that now with our vertical axis, a sub n. So essentially, we're going to kind of see more of a two-dimensional perspective of this sequence now, as opposed to just a one-dimensional number line. So I can see then I don't need to go any higher than 1. And now we'll go ahead and begin graphing our sequence. So now the nice thing about doing it this way is that I won't have to label these points now, because I'll clearly see exactly which a sub n corresponds to which n value. So a sub 1, for example, is going to be 1/2. Okay, a sub 2 was 2/3, slightly larger. A sub 3 was 3/4, 4/5, 5/6, 6/7. Notice I'm not being super precise here, but I do want to make sure I don't accidentally go past 1. So I'll put a little horizontal line there to be my guide. And I'm probably getting even closer than I should, because this should be, well, 10, that should be 10/11. Yeah, you guys get the idea. Okay, so then this is another great visual. We can see that as n increases, we can see that our terms of the sequence, a sub n, are getting closer and closer and closer to 1. We are visually seeing this as a horizontal asymptote. So we can see that the terms of the sequence are approaching 1, so we can again see that this sequence converges. So next is an opportunity for an exercise for you to try. So graph the sequence 1/3 to the n on a Cartesian plane, and then based on that graph determine whether the sequence converges or diverges. What you might want to do, since there isn't really a whole lot of space to work with here, is you can use this one that you have in your notes. You can just feel free to use that Cartesian plane, and if you'd like to just label it like I graphed a sub n, well, actually let me do it this way. This was the graph of n over n plus 1. I suppose you could call that a sub n if you wanted to, and then you could call the other one b sub n. It doesn't really matter, but if you want to go ahead and do this one in a different color, 1/3 to the n, starting at 1 to infinity. Let's just do the first term together really quick. So for example, when n is 1, I'd have 1/3, which is 1/3, which is about here. Okay, so go ahead and pause the video and finish graphing that sequence that we have at least going up to 10, and then based on that graph determine whether the sequence converges or diverges. Okay, so hopefully that went pretty well. Now if we plug in 2 for n, we'd have 1/9, which is going to be pretty small. And then we'd have 1/3 cubed, which is 1/27. That's even smaller. And then notice what's going to happen. This is going to get real close to the n-axis here. Okay, so of course it's never going to touch the n-axis, and it's definitely never going to cross the n-axis because it's not going to become negative at any point. So we can see then that as n gets larger and larger, the values of the sequence are getting smaller and smaller and smaller, and they are approaching 0, just like this was approaching 1. Okay, so we would then say that this sequence converges to 0. This one converges to 1. I should specify what it converges to. Okay, let's keep going. All right, so now we've actually taken a look of quite a few examples so far have been what we call a geometric sequence. Now, when you hear geometric sequence, you might not think much about that. Like, what about it is geometric? We'll later look at some applications, and you'll see why they're called geometric sequences. But a geometric sequence is going to occur if the next term of the sequence is obtained from taking the previous term and multiplying by a common ratio, which we're often going to indicate with an r. So really, a geometric sequence is an example of a sequence whose terms increase or decrease exponentially. So this, for example, is going to be a geometric sequence. Again, you know it's going to be a geometric sequence if you take consecutive terms and you divide them and you get a common ratio. So for example, let's actually go back up and look at some previous examples and see which ones might be geometric. So let's actually go back up to our list of ones that we had here in our example 2. And actually, we could even take a look at example 1. Notice to get from 1 to 1/2, I would multiply by 1/2. To get from 1/2 to 1/3, I'm not really sure what I would multiply by, but all I know is I would not multiply by 1/2. So you can see if you take the ratio of consecutive terms, like for example 1/4 divided by 1/3, reciprocate that and you would get 3/4. If I take two other consecutive terms, 1/6 divided by 1/5 would give me 5/6. Notice that these are not equal to each other, and so this is not geometric. Let's take a look at example 2. In example 2, notice that I go, and I almost even have it indicated here already, when I go from 1 to 1/2, I multiply by 1/2. To get from 1/2 to 1/4, I multiply by 1/2 again. 1/2 times 1/4 is 1/8. 1/2 times 1/8 is 1/16. So I'm multiplying by 1/2 each time. Similarly, you can take consecutive terms, for example, the 1/8 and the 1/4, find their ratio. Notice you get 4/8, which is 1/2. If I do that with the 1/16 and the 1/32, and notice I'm taking, oh, sorry, I should have done that the other way. It should be the n plus 1th term divided by the nth term here, or I guess the nth term divided by the n minus 1th term. You want the next one divided by the previous one. That's going to be what gives you that common ratio r. Otherwise, you're going to get the reciprocal of it if you do the opposite way. So this would be 16/32, which notice again is 1/2. So here, this is a geometric sequence where the r value is 1/2. I can see that that's not the case in part B, that the ratio of consecutive terms would not be a constant. I do not multiply by a constant value in order to get from the previous term to the next term. I guess technically C could be considered a, C is technically a geometric sequence because I'm multiplying by -1 to get to each next term. If you take the ratio of consecutive terms, no matter which one you do, notice you get -1 every time. So this is an example where the r value is -1. D is linear. Notice it increases by, so it doesn't increase by a common factor, but it increases by an addition of 2 every time, not a multiplication, right? So not geometric. Looking at E here, okay, we can see that we multiply, nope, we don't multiply by any common factor to get to the next one. We can see that we end up having n cubed, which is a power function, not an exponential function. Or I should use the term expression. It's a power expression, I guess, as opposed to an exponential expression. The Fibonacci sequence definitely is not geometric. Let's see. But part B here, notice, was a 1/3 to the n minus 1. And so it had powers of 3 in the denominator. So this is a geometric sequence where the r value, well, to determine it, you just take the ratio of those consecutive terms. Or you can think about, what do I multiply by to get to the next term of the sequence? So notice that we multiplied by 1/3 each time. Not only actually, not 1/3, but we technically multiply by -1/3 each time. If you're not quite seeing that, again, just take the ratio of consecutive terms and you'll see you end up getting a -1/3 value. Okay, let's see, have we done any other ones? This is not going to be geometric. You can see it doesn't have any sort of exponential powers, but this 1/3 to the n is very similar to that one that we just talked about. This one would have the r value of 1/3 because I'd be multiplying by 1/3 each time to get to the next value. Okay, so notice that we can write this geometric sequence in this particular form, where a sub n is going to be a times r, which is our common ratio, to the power of n minus 1. A is just our initial term of the sequence. So essentially our sequence, I'm going to actually write this in my sequence notation here. our sequence would be a, and then whatever a times r is, a times r squared, a times r cubed, a times r to the fourth, dot, dot, dot. That would be how we could kind of look at that. So if you take the ratio of all these consecutive terms, you essentially are multiplying by r each time to get to the next term of the sequence. Okay, now why do we care about that? Well, oftentimes we'll see geometric sequences come up in application problems, and like I said, we'll see some examples of that in future activities. But let's take a look at when a geometric sequence will converge versus when it will diverge. Because notice that we've seen quite a few of them. Right, this one, the r value is 1/3, and it converges. And if we keep going, this one, the r value is -1/3, and we saw that it converged. Let's look at this one. This was a geometric sequence. The r value was -1, and notice that it diverged, right? That was the one where it just kept oscillating between -1 and 1. And then this one was geometric, and the r value is 1/2, and notice that it ends up converging to 0. Okay, so that r value is going to play a big role in whether the geometric sequence converges or diverges. So let's think about what those are, like what the cutoff is, what r value makes it converge and what r value makes it diverge. So essentially, if r is between -1 and 1, then we're going to see it converge. We're going to see the sequence converge. And it's going to converge to 0. Well, let's look at the specific example. So let's talk about y first. So if r is between -1 and 1, then what we're going to see is exponential decay. The terms of the sequence are going to approach 0. Whereas if the r value is, say, 2, for example, if I look at the sequence 2 to the n, then that would be 2, 4, 8, 16, dot, 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 32, 64, etc. Notice that those are just going to increase and increase and increase, and so that sequence would end up diverging. So if r is greater than 1, which is it is in this case, then you're going to see exponential growth, and that means that the geometric sequence would end up diverging. Similarly, if r is equal to -1, you just end up seeing that oscillation between -1 and 1, and the limit doesn't exist, so the sequence diverges. If r equals +1, on the other hand, if r is +1, you would get the sequence 1 to the n. Now, the thing about 1 is that it to any power is going to give you 1. So this creates the very boring sequence, 1, 1, 1, 1, dot, dot, dot. And this sequence definitely converges because not only does it get closer to 1, it doesn't really get closer to 1, it is 1 all the time. So this is an example of where the terms of the sequence are the limit themselves, right? We know that the limit as n approaches infinity of 1 would just be 1. So we have a piecewise function essentially for that the sequence converges, the geometric sequence converges, as long as the r value is between -1 and 1. It will converge to 0 if r is strictly between -1 and 1, and it will converge to 1 if r is equal to 1. Let's take a look at an exploration here. I have a link to a Desmos applet. Close that. Okay, so here we can explore some different r values, and we see our starting point is r being 0.5, which is 1/2. And so notice that currently the graph of this sequence, we can see that this sequence ends up converging. The terms of the sequence are getting closer and closer to 0. Now I have a touch screen, and that allows me to use 2 fingers to kind of pinch together and expand one particular axis. If you don't have a touch screen, then you would have to adjust your axis by going to the graph settings, and then by simply adjusting your x value right here, which isn't too terrible, is it? So, but I kind of like the interactiveness of being able to use the touch screen. I'm going to go ahead and hide these labels just so we can see the sequence just a little bit easier. And so we can see that as we increase our n value, there's more terms of the sequence. Do more. you probably don't need more. You can really see that the sequence is definitely converging to 0. Okay, I'm going to slide that back here to maybe like 25 or so. Let's explore some other R values. So notice if I go to -1, for example, here is the graph of the sequence -1 to the n, the alternating sequence. And notice what happens is that as we increase the n value, it's not approaching anything in particular, it's just oscillating between -1 and 1, depending on whether n is an even or an odd number. So the limit doesn't exist and the sequence diverges for that particular one. If I increase the R value, notice, for example, if I do 0.9. 0.9 is pretty close to 1, but notice that it is just slightly less than 1, and so I still end up having this exponential decay. Essentially, my values are decreasing by 10% each time. You can kind of think of it like that. And so what happens is that we end up seeing the term still decrease towards 0, so the sequence converges. If I go to R equaling 1, notice again I get that very boring sequence of just 1. It's 1 no matter what the n value is. Now if I go up just ever so slightly, even to just 1.1, what I will start to see now is exponential growth. And what happens is that as my n value increases, my sequence, the terms of the sequence, increase exponentially. Right? So again, I'm using my fingers to zoom in here, or zoom out rather. But again, you could use the little gear and make this go up to like 2,000 if you wanted to. Okay, so we can clearly see that the terms of this sequence increase without bound, and so this particular sequence, geometric sequence, when R is even just 1.1, just slightly bigger than 1, ends up diverging. I could even do 1.01, and notice that it's not quite as extreme, but if I kind of zoom in, I can see that it still increases without bound, especially as I go and increase the n value here. Still increases without bound, just not quite as extreme as the 1.1 did, of course, because that's going to grow even faster. Okay, I hope that that helped. Now, another thing that we can kind of think about is, I mentioned so far how, and we've seen, how the graph of a sequence is just a set of, actually let me show you a negative R value, so you can see that also. And then I'll talk about what I wanted to talk about. So notice that when our R value is a negative number, what we have is we still have that oscillation, but notice that that oscillation eventually just becomes insignificant as the n value increases and our terms of the sequence end up approaching 0. So what I wanted to also show you was that, so here's R equals 0.5. So notice as these are just distinct points, right? This is not a continuous function. It's not an actual curve that's connected. But if I look at the function itself, I essentially can connect the dots, and whatever happens to the function as x approaches infinity will be the same as what happens to the sequence as n approaches infinity. We're going to get to a theorem about that in a little bit. Right now, actually. So that theorem tells us that if the limit as x approaches infinity of a function equals L, where L is our limit, and then we can think of a sub n as being a function of n, then the limit of the sequence is that same limit, L. We've kind of been doing that already, but this just kind of puts it in a more formal approach. Now, if you also recall from Calc 1, from differential calculus, we know that as x approaches infinity, 1 over x to a power is going to approach 0 as long as that exponent's not negative, right? If it's a negative exponent, then we'll end up reciprocating and then it'll end up growing, which is not what we want. But so if this was like a squared, a cubed, a square root, anything like that, then that limit is going to be 0. So then similarly, we can see the same thing happening with n. We've already done a few examples of that happening. So again, it's just putting it in a more formal form.